All right, we're ready to meet up with our final thermodynamic function, which we will call the change in free energy, or delta G, shortly. Right now, what we know about the second law of thermodynamics is that delta S for the universe needs to be positive for a thermodynamically allowed or spontaneous process, right? The difficult part about that phrasing is that it includes the universe, right? And the universe, somewhat by definition, is a very large place, after all, okay? It would be easier if we had something we could use to figure out whether the reaction is spontaneous that was just a state function of the system, because we've seen we have some relatively simple ways to calculate values for state functions of the system, okay? What we're going to do is we're going to define a function that satisfies that need or that desire. It's called the free energy, or sometimes the Gibbs free energy, because there are also some other slightly different free energies. Gibbs is the name of a person who was important in the development of these ideas. So the free energy definition is just that G, the free energy, is equal to H minus T times S, okay? H, T, and S, everything on the right-hand side is a state function. G is alone on the left-hand side, so that means G is definitely a state function, okay? If we take that and consider a reaction that takes place at constant or near constant temperature, then essentially that means when we take delta G, we can pull the T through the delta, just like you would pull a constant through the derivative, and say delta G is equal to delta H minus T delta S. That's a sort of central equation for thermodynamics and chemistry, that one on the bottom of the screen, okay? We already know how to calculate delta H and delta S. Right? And so that gives us one route to finding delta G. If we know those, we could find delta G as a function of temperature. Right? Notice delta G will vary with temperature because there's a T in its definition after all. All right, so let's look at how this delta G is related to delta S for the universe, okay? Going to do a little bit of deriving here, okay? So our first equation says delta G is delta H minus T delta S. We want to compare this with delta S for the universe, because that's the thing right now that we can relate to spontaneity, okay? Delta S for the universe is delta S for the system plus delta S for the surroundings, because the universe is always just the system plus the surroundings, okay? Here, I've dropped the system tag because that delta S is actually the same delta S for the system as the delta S that would be up there in our equation, right? We normally don't write a system tag on a system property, okay? So that says that's the delta S that we already want. So that's the first thing we can see that's in there in delta S for the universe. That's also in our equation here. Delta S for the surroundings, we want to convert that into something that's about the system, okay? Delta S for the surroundings, we're at constant temperatures. That means we can say that's Q over T for the surroundings, okay? Q for the surroundings has to be minus Q for the system. Okay, so I can replace Q for the surroundings with minus Q for the system. So now I'm at least getting towards system properties, okay? Lastly, what I have in the equation for delta G is I have a delta H. Right now I have a minus Q, I have a Q for the system. So if I'm willing to say I want my reaction to happen at constant temperature and pressure, okay, that means that basically in something that's open to the world. So its temperature should stay reasonably constant and its pressure will remain constant, because any gases that are made will just expand out into the surrounding volume. I can say that minus Q for the system over T is equal to minus delta H over T, right? Because at constant pressure, remember that delta H is equal to Q sub P, right? Which the way we're writing right now, we might call that Q system at constant pressure, okay? So this now says that's equal to delta S for the surroundings. So what I'm going to do now is I'm going to take this term, right? And I'm going to bring it up there and put it in for delta S for the surroundings, okay? So that gives us delta S for the universe equals delta S for the system minus delta H over T. This is now getting to look more like what we have up here, okay? It's at least got the right things in it now, right? It's got H and T, and it's got delta H and delta S and delta T all in there. So I can say that T delta S for the universe, just multiply the equation with the arrow pointing at it, multiply this equation through by T all over the place, right? I get T delta S for the universe is equal to T delta S minus delta H, where those things on the right-hand side are all for the system, okay? We need a little more room, so let's bring that equation with us. These are the two equations that I have. That was the equation on top is the one that defines delta G. The second one there, the one underneath it, is the one that now we worked our way towards, okay? Look at the right-hand side of those equations, all right? The right-hand side of those equations differ only in sign, right? If I take delta H minus T delta S and multiply that by -1, I would get T delta S minus delta H, right? So what I've proven here is that delta G is equal to minus T delta S for the universe. Okay. Now, delta S for the universe, the sign of delta S for the universe tells us whether the reaction is spontaneous or not, right? The temperature is always positive because our temperatures in all these equations, they have to be absolute temperatures, right? So they're Kelvin temperatures, they can't be negative. So that means for spontaneous reaction, I want delta S for the universe to be positive, and that means that I need delta G to be negative, okay? So if delta S for the universe is positive, then up here I will have positive, positive, and the minus sign in front of there, right? And so that means that whole thing will come out negative in that instance, okay? So that means when delta S for the universe is positive, delta G for the system has to be negative, okay? That says we can use delta G for the system as an indicator for whether the reaction is spontaneous or not. We no longer have to calculate delta S for the universe in order to make that call. So this is why delta G is a very useful thing. For a lot of chemists, delta G is sort of our favorite thermodynamic state function. Delta G is a state function of the system that, as we'll see momentarily, makes it easy to calculate. We get another one of those sum for the products minus sum for the reactants equations. And the sign of delta G tells us whether the reaction is spontaneous, okay? The fact that it's called free energy, that sometimes bothers people, but there's a reason for that. The value, the magnitude of delta G, when delta G is negative, the absolute value of that tells us the maximum amount of useful work that you could achieve by exploiting that reaction. So essentially, if you had a reaction taking place under the conditions we use for delta G, constant temperature and pressure, the magnitude of delta G would tell us what would be the work you could accomplish with that if you could build a perfectly efficient engine to run on that process. Okay, it's sort of like the available energy is the meaning of free in this case. So delta G essentially accounts for the fact that some of the thermal energy will always be lost to entropy. And so that's where the minus T delta S piece in that equation comes into play. That's why it's called the free energy. So let's look at how delta H and delta S influence whether the reaction is spontaneous, okay? We know we want delta G to be negative now for our reaction to be spontaneous, okay? So we can look at the form of the equation that connects delta G to delta H and delta S and see what are the desired signs for those two quantities, right? We kind of have hinted at this before because we have this sort of sense that, for example, exothermic reactions seem like a good idea, right? And now we can make certain that that's actually correct. So if delta H is negative, the reaction is exothermic, right? If delta H is negative, then that first term on the right is going to be negative. So then that term is going to be helping to pull delta G towards a negative value. So exothermic reactions, that would favor the reaction being spontaneous, okay? Doesn't guarantee it being spontaneous, but it does its part, right? The enthalpy term then at least is in favor of it being spontaneous. Then I go to the entropy term. It's minus T delta S. And again, T is always positive, right? So that says for minus T delta S to be negative, if T is positive, I also need delta S to be positive. So delta S is positive. That means entropy of the system increases. That's a factor in favor of the reaction. Right? So my reaction is more likely to happen if delta S is positive. That's going to help it to be spontaneous. Okay, so that says that I have two factors, delta H and delta S. They might agree with one another, in which case the outcome is obvious, or they might disagree, in which case the fact that S is multiplied by T in that equation will be the determining factor. So let's look at a little more detail how that would work. There's a lot in this table, so take some time with it and do look it over, okay? Delta G is delta H minus T delta S. So we're looking at what delta H and delta S and the temperature, the three things that are on the right-hand side, how do they play off against one another, okay? If delta H is negative and delta S is positive, then no matter what I put in there for T, given that T can't be negative, then delta G will always be negative, right? Because the first term, if delta H is negative, then that first term is negative. If delta S is positive, then the second term is also negative. So if both terms are negative, then no matter what temperature I put in, delta G is negative. So that reaction is always spontaneous. Essentially, the two factors, delta H and delta S, are both in favor of the reaction. Second row, if delta H is positive and delta S is negative, then both factors are actually against the reaction. That says there's no temperature I can put in that would make it spontaneous, right? Because then if the first term is positive and the second term is positive, then the combination of them is always going to be positive, right? And so there's nothing I can do to make that reaction be spontaneous. The sometimes more interesting cases come when the signs of delta H and delta S are the same, because that means that I have one factor in favor of the reaction being spontaneous and one against it, okay? If they're both positive, that says delta H's piece is making the reaction tend to not be spontaneous, but delta S is in favor, right? So what happens? Delta S wins when the temperature is high because T is multiplying delta S, right? So if both signs are positive, then at some point there'll be a temperature at which delta G becomes negative. It might be a very high temperature, it might not, but there'll be some temperature above which delta G is negative and the reaction is spontaneous. So we say that process is spontaneous only at high temperatures. If both signs are negative, that says now delta H is in favor of the reaction, delta S is against it. At high temperature, delta S wins. So in this case, at high temperature, the reaction stops being spontaneous. If I want that reaction that has both signs being negative to be spontaneous, I need to keep the temperature lower because that's where delta G will be negative, okay? Like I said, do spend a little bit of time looking at that and make sure those ideas make sense to you, okay? It's really just looking at the equation and keeping in mind that the thing that dictates whether it's spontaneous or not is delta G negative. Okay, and from the sign of delta H or delta S, we can tell what the signs of each of the two terms would be. The other thing to remember is just that T, because it's a Kelvin temperature, is always positive. All right, so delta G values also appear in your thermodynamic tables, like the ones you've been using to look up heats of formation and entropies. I should probably have put the little thing on there, so let me write that in, okay? I can look up, when I look up delta G's, what I find are delta G's of formation. They have that subscript F again. That means it's delta G for the same formation reaction, the reaction that makes 1 mole of the compound from elements in their standard states. Among other things, that means the delta G of formation for an element in its standard state will be 0, just like for the delta H of formation. So there's two ways we could calculate delta G for a reaction. One way is with this equation, which is really just the delta G equivalent of the equation we used for delta H, right? The sum for the products minus the sum for the reactants, everything multiplied by the numbers of moles, okay? If you use that equation, because the delta G's of formation are defined for being at 25 degrees C, the result you get is delta G at 25 degrees C. Remember, delta G is going to change if we change the temperature, okay? We generally are willing to assume that delta H and delta S do not change with temperature, okay? That's a decent assumption. It's not perfect, but it's a decent assumption for most reactions, okay? Delta G, on the other hand, generally will vary pretty sharply with temperature because after all, there's a T in the equation that defines delta G, right? So it's not surprising that it would change with temperature. If I want to know delta G for some temperature that is not 25 degrees C, then the only way to find it is to use the formulation that says delta G is equal to delta H minus T delta S. Okay, if I want to know delta G at 25 degrees C, I could use either one. I could use the delta H minus T delta S equation and just put in 298 for T, or if I had the delta G's of formation handy, I'd probably do it that way. Kind of depends what information I have looking at me if I'm at 25 degrees C, right? But if I'm at any other temperature than 298 Kelvin, then I have to use the delta H minus T delta S approach to try and find delta G. Okay, people get confused by that, so be on the lookout for kind of crossing those up. All right, one more warning, and then we're going to do an example to finish this out. Okay, if I look at the data for nitrogen from the tables, okay, if I look in Appendix E in the textbook, say, and I get the values for nitrogen, I'll see that the heat of formation delta HF is 0, delta GF is 0, because those are for the formation reaction, right? The entropy S naught is not equal to 0, Okay, and so the data in the table, that's the absolute entropy and not the delta S of formation. So those values, again, are not ever zero. Another thing that I've seen students do is if you if you have two of these values and you're trying to find the third one, okay, you cannot do it this way. Okay, it's a little bit tempting if you're thinking there's that delta H minus T S something equation, but it doesn't work. Okay, as you can tell, if you just look at those numbers, it is not gonna get me there if I stick things in like that, right? And so well, just don't do it that way because it doesn't work. All right, I'm going to do two more calculations from this this nickel carbonyl reaction that I calculated some things for in the previous video. Okay, the delta H and delta S up there are the things that I calculated earlier. Now I'm going to do two separate things. I'm going to calculate delta G of formation for the product, right? Given delta GF for CO. Okay, delta G of formation for nickel will be 0 because the nickel is an element in its standard state. Okay, I didn't put that explicitly on the screen, but nickel metal, nickel solid, that's going to be a standard state because that's what nickel would be if it was at room temperature and pressure, right? So first I'm going to find the delta GF for the product. Then I'm also going to find the range of temperatures at which this reaction would be spontaneous. Okay, then we'll talk briefly about an application of this reaction after that. All right, let's do the calculation. This first part is actually a little bit tricky. It says I want to find the delta G of formation for this. Okay, so if I've never done this problem before, and if I didn't have a piece of paper sitting next to me with the answer, this maybe is a little bit of a head scratcher at the outset. But what is the only equation we can write based on this reaction that has that delta G of formation in it is that delta G for the reaction should be equal to what? The delta G of formation for the product. That's the thing we're trying to find. Minus delta G of formation for nickel minus 4 delta G of formation for the CO, right? And if I do it that way, the thing I have to remember, the thing that makes this a tricky problem is the delta G that I get then is the delta G for 298K. Okay, so then I can put over here that that's equal to delta H minus T delta S, where my T needs to be 298K. So that's how we're going to go about this. All right. This is not an obvious problem. Most students find this this particular kind of problem a hard one, basically because first I'm going to have to find the delta G at 298 and then use that to solve the actual question that's asked. All right, let's do it. So doing just what I said, first I'm going to find delta G as delta H minus T delta S. I have to watch out for units here because my delta H is in kilojoules up there, 160.8 kilojoules. I'm going to write it in here, minus my temperature, I'm putting in 298K. My delta S up above is in joules, so I'm going to make that into kilojoules. So I'm going to make 409 into 0.409, because then it's in kilojoules per Kelvin. So now I have kilojoules for both terms, right? And I have notes over there that say this is 38.8 kilojoules. Okay, that's delta G for the reaction at 298K. Why do I need that? Because that's the delta G. Delta G at 298 is equal to delta GF for the product. Sorry, there's a bunch of parentheses in there. I keep stumbling on writing them. And this thing is also equal to minus 38.8, we know now. Okay, so that gives me an equation I can solve because I know the value for CO. This one is going to go to 0 because the nickel is an element in its standard state, right? Because it's solid nickel up there. So that says I can rearrange and solve this for delta G F for the product, the thing I'm after. Come on, pen, you can do it. That's equal to the minus 38.8, the delta G for the reaction, plus delta GF for the nickel, which is still going to be 0, but I'll write it in one more time, plus 4 delta GF for the CO. And that's equal to minus 38.8. Come on, I drew an 8 there. Really, I did. Plus 0 plus 4 times, what is this number? Minus 137 up there. And all of that, according to my notes over here, is equal to minus 587.8.5, rather, sorry. It doesn't really matter. And that would have units of kilojoules actually per mole. The per mole will bother some of you. The things we look up in the table will come with a per mole because they're per unit quantity. In this case, that's really kind of hard to see because essentially it says there's a 1 mole piece in front of this, and that's what there's a 1 mole piece kind of implicitly in front of there, and that's where the per mole ends up coming from. But it should match the units that were on the other, the ones we're given up here, right? So it should come out the same units as that. All right, that's sort of a separate side piece of the question, just because it's a little bit of difficult calculation. I confess it's the kind of question I have at times liked to ask because it requires a little bit of cleverness to figure out. The other part of the problem said to find what temperatures is the reaction spontaneous, given that we know delta H and delta S, okay? Delta G is equal to delta H minus T delta S, okay? That's always got to be true. We know that delta G is negative at 298, right? And so at 25 degrees C, our reaction is spontaneous according to that, okay? Delta S is negative. That means delta S is against the reaction. So if I raise the temperature, at some point, delta G is going to become positive. It's going to stop being spontaneous, okay? Because this, my signs are both negative. That says my reaction is spontaneous at low temperatures, meaning below some value. Delta G is negative below a value, it'll be positive above it. Delta G is a continuous function, it turns out, and that means delta G will have to pass through 0 in between. So what I want to do is say set delta G equal to 0, and that's going to let me solve for the temperature where the sign of delta G changes. That'll give me delta H equals T delta S. Then I can say T equals delta H over delta S. Once again, I have to be a little careful about my units. Minus 160.8, and that's in kilojoules, which means down here, minus, I'm going to put this in kilojoules again, so I'm once again going to make it from 409 into 0.409. That's now in kilojoules per Kelvin, so when I divide them, I'll get Kelvin, and that comes out to be 393 Kelvin. If you do forget to fix the units there, you would get, the good news is you'd get a temperature that's kind of crazy, right? In this case, I would get 0.3 Kelvin. And if I get 0.3 Kelvin for almost anything, I should stop and ask myself, can that possibly be the right thing? And in this case, the answer is definitely no, since I know that it's spontaneous when the temperature is 298. So that can't be the temperature where it switches. So in this case, this is spontaneous for any temperature below about that 393 Kelvin. Right. And again, the reason it's below is because the entropy term delta S is the one that is trying to basically turn the reaction off. So if the temperature gets too high, the delta S will dominate the delta G equation. My reaction would stop being spontaneous. Okay. Going to finish this out with a little bit of application for this. This reaction, the reason why I'm playing with this reaction is because it's actually used in the metallurgy industry for purifying nickel. It has a name. It's called the Mond process. If we wanted to do this, a quick explanation of how this would work. I'd have some sort of ore or something, some rocks basically that have nickel in them, okay? The one thing that makes this work is that most other metals would not undergo a reaction like this, okay? That part where it converts the metal into the gas phase, that's kind of an unusual thing, that product, right? So if I have a sample that's got some nickel in it and I react it with carbon monoxide, the nickel can be swept up out of the solid phase and into the gas phase. So I would take my ore and I would grind it up into a powder probably to make this go at a reasonable speed. But then my nickel will be lifted up into the gas phase. My other stuff that was in the rocks is left behind, okay? I want this reaction to go spontaneously forward, so I just have to keep the temperature below about 120 degrees, 120 Kelvin rather. Wait, temperature below 120 Kelvin, that's not right. 120 degrees C, sorry. Below about 120 degrees C for the reaction to go forward. Typically, that's done at about 50 degrees C, okay? It has to be above 42 because that's the boiling point for the product, and we want to make sure the product is a gas because that's what's making this step work, right? Is getting the nickel up into the gas phase. Once that's done, now my nickel is in the gas phase. So all I have to do to separate the nickel from the other stuff is to either pump the gas out of the container or just mechanically somehow remove the solid by having some little sweeping thing push it out of there, okay? If I remove the gas, then I have gas that's a mixture of CO, presumably, because I probably put in excess CO, and I have the nickel carbonyl. Now I want to get the nickel out of there, right? I don't want to have that nickel carbonyl compound. I want nickel metal. So to do that, I want to make this reaction go backwards. We actually just learned how to do that, right? If I want to make the reaction go backwards, all I need to do is raise the temperature up above that 120 degrees C target. Because when I do that, delta G becomes positive for the forward reaction, the reaction the way it's written here. But if delta G is positive for going in that forward direction, then delta G has to be negative going in the opposite direction. Basically, if it's uphill one way, it has to be downhill coming back the opposite direction, right? It can't be uphill in both directions. So this says if I take the temperature up above about 120 C, common industrial practice, I'm told, says a little over 200 C. Then delta G for the forward reaction is positive. That means delta G for the backward reaction is now substantially negative. My reaction goes backwards. And this is the neat part where you would have a container filled with gas and you raise the temperature out of it and little drips of nickel would just come basically precipitating or falling down out of the gas phase and redepositing themselves as solid. Once that happens, I can pump the CO out of the container and get the nickel, okay? It's a really interesting process, and it takes advantage of the fact that by changing the temperature, we could make this reaction go in either direction, however we wanted to. It just so happens in this case that the temperature where it switches is one that's not so hard to get to, right? 120 degrees C is not crazy hot. It's not ridiculously expensive to heat something up that high. So it is a process of some practical value.